What do you think when you see a vector represented by these coordinates? Probably I can draw it in the coordinate system. 4 steps to the right, 2 up, done. Okay, but what if we hide the coordinate system and draw an arrow of the same length and same direction somewhere else? Is that a different vector? No, the vector is still the same. This here is just a representative of my vector. Geometrically speaking, a vector is the set of all arrows that have the same length, are parallel and have the same orientation. In other words, a vector consists of infinitely many arrows at the same time. They are characterized by length and direction. As long as these stay the same, the vector can be shifted arbitrarily. A single arrow from this set, this one, or even this one, is called a representative of the abstract vector V. Vectors in the plane are 2-dimensional, whereas vectors in the space we are familiar with are 3-dimensional. If we place a representative at the origin of a coordinate system, we call it a position vector. It then points from the origin to the point. This is almost always done in linear algebra, in order to visualize vectors and to read off their coordinates directly. That means these here are the coordinates of the position vector with respect to this basis. If I were to choose a different basis, essentially a different coordinate system, for example this one, then the coordinates of my representative would be different, even though the underlying vector is still the same. If nothing else is specified, however, the standard basis is usually assumed. Okay, this arrow, let's call it Victor, is, as I said, only a representative of the actual abstract vector. In practice, the term representative often disappears and people simply call the arrow a vector. So, Victor the vector, even though that is strictly speaking not entirely correct. However, we can only make the abstract vector visible in the coordinate system by choosing a representative, that is, a concrete arrow such as Victor here. This allows us to distinguish between 2 important roles, the position vector, which you just saw, and the displacement vector. Let's take as an example the vector described by these coordinates. One representative of this vector can be drawn as an arrow from point A to point B. For example, you go 100 meters east and 50 meters south. This arrow can be placed anywhere and does not have to start at the origin. It describes a displacement and is therefore called a displacement vector. The same vector can just as well be represented by another arrow, for example from point C to point D, as long as the displacement is still the same. The instruction go 100 meters east and 50 meters south works the same everywhere, whether you are standing in New York, Tokyo or anywhere else. Displacement vectors, for which only direction and orientation matter, meaning the length is not in focus, are called direction vectors. For example, when describing directions of motion, go in this direction. To make calculations even easier, their length is often normalized to 1, as we see with the vectors of the unit basis, for example. Now you know how a vector can be interpreted geometrically. Depending on the context, it is represented either as a position vector from the origin or as a displacement vector from one arbitrary point to another. Okay, now you can add vectors by adding their representatives. For example, consider these 2 vectors, which we visualize here as position vectors. To add them, I place the start of the second representative at the end of the first and draw a new arrow from the origin to the final endpoint. Mathematically, this corresponds to adding the first components and then the second components. I go 2 steps to the right and then 4 more. I go 3 steps up and then 1 down and end up here. That is vector addition, and it works in exactly the same way in any dimension. Subtraction works very similarly. In fact, it can be understood as addition with the opposite vector. I simply add the negative of the second representative, which has the same length but points in the exact opposite direction. Okay, the next important operation is scalar multiplication. Scalar multiplication stretches or shrinks the vector, or even reverses its direction. If I double the length of the representative and those of the abstract vector, I double all its components. If I halve it, I halve all its components. And if I multiply it by a negative number, the vector also flips its direction. The length of a vector's representative is essentially its size. If the components represent, for example, forces in the x, y, and z directions, then the length, the magnitude, corresponds to the total force. The length of Victor here, for example, can be computed using the Pythagorean theorem in the three-dimensional space. For 2 dimensions, it works accordingly, and so on. Okay, now the next important point. Vectors do not have to be representable by arrows. They can have arbitrarily many dimensions, and the components can describe arbitrarily things, not just position, force, or velocity. It can really be anything at all. And that is exactly what makes vectors so cool. Suppose, for example, you are a big role-playing game fan and create a character for your game. Your character has the following attributes: strength, health, intelligence, dexterity, and charisma, each with some point value. Now you can combine these values into a 5-dimensional vector. That is an ordered list. The length then corresponds, roughly speaking, to the overall strength of your character. The larger this value, the more experienced the character. Mathematically, this length is called the norm of the vector. In this case, it is the Euclidean norm, the standard length in Euclidean space. That means the space you are familiar with. This is exactly the same idea you saw earlier in 3 dimensions, just extended to 5 dimensions. To distinguish this norm from the absolute value of a number, we generally use 2 vertical bars. Okay, now after a fight, your character gains new experience points. This means the fight produces a new vector represented by this ordered list, which can now be added component-wise to your previous state. Scalar multiplication scales all attributes without changing their ratios. Maybe your character levels up and all attributes grow by the same factor. If the character grows by a factor equals 1.1, all values increase by 10%. But the build, the overall profile of the character stays the same. Even though these are not arrows in the geometric sense, you can still imagine this as a 5-dimensional arrow. If your character mainly gains strength points, the strength component grows, and the direction of this abstract arrow increasingly points toward the strength axis. As you can see, vectors are extremely versatile. Different fields use different representations. In physics, you cannot avoid using arrows. In computer science, vectors are usually treated as ordered lists, like these character attributes. Mathematicians in the end simply prefer writing V with an arrow on the top. Then V is just an element of a vector space and can be represented by coordinates with respect to a chosen basis, usually the standard basis.